starting, right? Well, it's
usually when I'm going to London, I'm not worried about which space anymore. So
Good morning, everyone. And a big welcome to HaskellX 2017. We, on the committee here, and of course Skills Matter, who's organizing this, extend a very big thank you to all of you who are here. Before we start, I thought we'd mention we do have a code of conduct. It's available online. Please follow it. There are fire exits, so please be aware of those in the back. And in the event of a fire, follow fire marshals. For the latest schedule, so you'll have a printed schedule, but for the latest one that's updated with all of the latest lightning talks and prerequisites for workshops, look online because it's been updated there. We'll also be collecting feedback at the end of each session. So when you leave the session, go out and you'll find a little box. Drop a single colored Post-it note into that box outside the room to give your opinion of that session.
Okay, it's my pleasure to introduce our first keynote speaker. So unfortunately, Julie reported this morning that she is not feeling well, and we are very much hoping right now that she can still make it for the afternoon. But we are going to have Gabriel's keynote first, and it's very nice of Gabriel that he was willing to flip on such short notice. And so it's now my pleasure to introduce Gabriel Gonzalez, who is probably one of the most well-known persons in the Haskell community. He has been blogging and working on about every imaginable topic. And he's currently working for Awake Security, and they're using Haskell there as well. Mm-hmm. And I'm very curious to hear what you have to tell us today. Yeah. So please welcome Gabriel.
Thank you very much for the very gracious introduction. I also like to thank the organizers for giving me an opportunity not only to speak here, but to meet with all of you. I'm looking forward to all the conversations that we'll have today and tomorrow. So, like you mentioned, not only do we use Haskell at Awake Security, we actually use Liquid Haskell, which you can think of as an extension to Haskell's type system. And today's talk is going to be about how you can turn runtime bounds checks into static compile time bounds checks using Liquid Haskell. I would like to begin this talk by describing what I call the golden rule of programming, which is that if something can go wrong, there are two ways that you can fix the problem. You can either push the problem downstream or push the fix upstream. And you should always prefer pushing the fix upstream whenever possible. The example I like to use to motivate this is the head function from Haskell's Prelude. This is a partial function that will fail on empty lists. And it'll fail with the runtime error, which is difficult to catch. And there are two ways that we can make head safe. One way is that we can just push the problem downstream. If head receives an empty list, we return a nothing, and we force downstream consumers to figure out what to do with that case. So we've deferred actually solving the problem. Another thing we can do is we can push the problem upstream and just require that head is called with a non-empty list. And there are several ways you can do this. For example, you could use the non-empty data type from Haskell's base libraries. But today I'm going to talk about how you can use Liquid Haskell to push requirements and preconditions upstream. Here's an example of a Liquid Haskell type signature, which says that head is a function from a list of A's to an A. And we can name this list of A's, we can call it X's, and say that, and attach a predicate, which says that the length of X's must be greater than or equal to 1. And now head only works on non-empty lists. And we'll get a compile time error if we try to pass in an empty list. You can think of Liquid Haskell as a backwards compatible extension to Haskell's type system. You can use it to add type-level predicates anywhere within your type signature. However, it's not integrated directly with Haskell's default ordinary type signatures. You have to keep the Liquid Haskell type signature side by side with the original ordinary Haskell type signature. And you store it basically as a comment, which uses @ symbols to indicate to the Liquid Haskell type checker that it needs to specially process this comment. So you can see there's a Liquid Haskell type signature for head, and then the ordinary Haskell type signature for head. Here's another example which I'm going to be using throughout the beginning of this talk, where the absolute value function. So we can not only refine inputs, but we can refine outputs as well to attach information to them. So we can say, for example, that the absolute value function returns an integer named n such that n must be greater than or equal to 0. Here's an example. Let's say we want to test drive this, and let's actually quickly, should open up a terminal and make it bigger. 1 second. Sorry. All right, so let's say I run, first open up a Nix shell, so I have the liquid Haskell type checker. Okay, liquid, totality, and the example I want to type check, like head.hs. And this is a later example which fails. Let me actually do the first example which should pass. So I call that. Can people see that? Is that readable? Yeah. So this is what it looks like when the program passes. So liquid Haskell does several checks on it and then declares the program is safe. And safe in this context means that the program at the term level obeys the specification, the liquid Haskell specification at the type level. Oops, how do I return back to there? So that's a very quick intro. And for the rest of this talk, I'm going to structure it into 3 main sections. The first part will be the majority of the talk. So about half the talk, 50%, will be liquid Haskell 101, talking about the basics of how it works and how you can use liquid Haskell as a type checking tool. And then about 40% of the talk will be showing how we use liquid Haskell at Awake Security to do high-performance protocol parsing and verifying that it's safe. And then the last 10% of the talk will show you how you can contribute to the liquid Haskell ecosystem if this is a project that excites you and you want to see it go places. So liquid Haskell lets you annotate types with predicates. And if you annotate the input type of a function, you can think of that as a precondition, like you learned in your computer science classes. So like head has a precondition that the input list must be non-empty. If you annotate a function output type with a predicate, you get a postcondition. And that adds additional information which can be used by downstream components to prove additional preconditions. So preconditions are free, meaning that you can always add more preconditions to a function, and liquid Haskell will always accept them. That just means that it will add more checks to the function every time you call it. And so there's no restriction on how many preconditions you can add to an input. And liquid Haskell will enforce those preconditions at compile time. So again, the example I showed before, So here in this same program, I'm calling the head function on an empty list. And normally in Haskell, if you did that, you would get a runtime type error. And then it would also not only be weird, but you'll say like, error partial head. I don't remember what the error message is, but it's really hard to actually track down where you called the head function that failed. With liquid Haskell, you can find out exactly where it failed, and you find out at compile time, which is very handy. Here's an example of what an error message looked like for liquid Haskell. I don't expect you to understand the full error message, other than to point out that liquid Haskell statically knows that the length of this list is 0, and then it says, but you told me that the input to head needs to have a length of at least 1, therefore this is the compile time error. And the key thing I want to point out in this example is that with liquid Haskell, you can make your code safer without making any term level changes to your code. If you've used Haskell a lot, you're used to the idea that in order to make your code more type safe, you need to make term level changes, like wrapping things with new types, maybe using a different data structure, like using non-empty instead of list, or in the extreme case, using template Haskell to add additional compile time checks. And I feel like these are really just workarounds for deficiencies in Haskell's type system. And liquid Haskell takes the philosophy that rather than trying to change our term level code instead of pushing the problem down into the term level code, let's push the fix upstream and fix Haskell's type system and make it more expressive so that we don't need to change our term level code to make it safer. Another thing you can do with liquid Haskell is attach postconditions. The example we gave so far is the absolute value function, where you can assert at the type level that it's going to always return a positive number. And here I've combined the absolute value function with the head function in this example. And I say, example is a function from an integer to another integer. So the input integer we'll call x. And then we say, if the absolute value of x is less than 0, then call head on an empty list. Otherwise, return x. So I'm going to ask the audience a question. Do you think that this example will type check or not type check if I run liquid Haskell on it? Raise your hand if you think it will type check. OK, about a third of the audience. Raise your hand if you think it will not type check. about another third of the audience. So ones that are volunteering not to answer, they're not sure. So the answer is that this will type check. And the reason why is that liquid Haskell is smart and knows that the absolute value of x is never going to be less than 0. Therefore, the then branch of the if-then-else expression will never be evaluated. Therefore, this head function, therefore, we can ignore the fact that head is being called unsafely on an empty list. So liquid Haskell is, in effect, using a post condition to verify that a precondition is met. And we can actually go a step further. Because liquid Haskell statically knows that we're always going to take the else branch of this if-then-else expression, then it knows that we can add an additional post condition to our type signature that asserts that our example function is the identity function on integers. So here he says, example is a function that takes an input integer named x and returns an output integer named y such that x equals y. So normally the only way you'd be able to assert that something is identity function if it was parametric, like the polymorphic identity function. But here we can actually assert that a monomorphic function is identity function, which is something really neat and very difficult to do in ordinary Haskell. So the thing about preconditions is that, postconditions, is that you can only prove postconditions in 3 possible ways. So one way is that you prove it from a precondition. So for example, let's say we have a trivial identity function on non-negative integers. So this function has a precondition, which specifies that the input should be not negative. And since it returns that same input, then we can trivially prove the postcondition, which says that that result is still not negative. Another way that we can prove a postcondition is we can cheat. And we can say, I'm going to tell you that this postcondition is true. In fact, there are several such assumptions in the liquid Haskell prelude. So here's an example of an assumption which states that for the less than operator in Haskell, takes 2 arguments, called x and y, and returns a bool named z such that z is true if x is less than y. And one thing I want to point out here is that the less than operator on the left is not the same as the less than operator here on the right. The one on the left is the term level less than operator. The one on the right is the type level less than operator. And liquid Haskell, by default, doesn't actually know that there's a connection between the two. The type level less than operator is something that's built into liquid Haskell, but the term level less than operator is not. So you need to add such an assumption in order to establish a connection between the term level world and the type level world. And this is a way that we can promote information from the term level world to the type level world. And the second assumption is very similar. We use an assumption to promote information about term level subtraction to type level subtraction. And then so the third way we can prove a postcondition is just by combining postconditions that we've already proven or asserted using an assumption. So for example, the way we were able to prove that the absolute value function always produced a non-negative result was because we had assumed certain things about how less than worked or how subtraction worked. And then liquid Haskell was able to chain together those deductions to figure out that the function produced a non-negative value. To make that concrete, let's walk through a specific example. So here I have the absolute value function, which takes an input of x of type integer. We don't know anything else about x so far. It's just an integer. But we do know something about the numeric literal integer, the numeric literal 0. We know it's an integer n such that n equals 0. Liquid Haskell will automatically promote term level numeric literals to type level numeric literals. And if we combine the promotion of 0 with the promotion on the previous side of the less than operator, then we can promote x is less than 0 to a type level x is less than 0 inferred type for that expression. Similarly, we know that 0 minus x is a term that we can promote to the type level. It's an integer n such that n equals 0 minus x. So it's almost just like reflecting the term level to the type level. And then finally, liquid Haskell has built-in support for if-then-else expressions. So it can then infer that the type of this if-then-else expression is quite rich. It says this is an integer n such that if x is less than 0, then the result will be 0 minus x. And if x is not less than 0, then the result equals x. And so you notice that this refined type is much stronger than what we were trying to prove in our original postcondition. We only asked liquid Haskell to prove that n is greater than or equal to 0. But liquid Haskell actually knows a lot more information. So it knows that if you call the absolute value function on -1, the result is going to be 1. And not just greater than or equal to 0, 1 specifically. But Liquid Haskell is smart and can figure out from the richer type signature, we can still infer simpler type signatures. This is called subtyping in Liquid Haskell terminology. So Liquid Haskell can infer richer types are subtypes of simpler types like this one down here. And it does this automatically through the use of an SMT solver, such as Z3, which is you have to install whenever you use Liquid Haskell. And what's nice about Liquid Haskell is the fact that this solver can do these deductions automatically for you, and that makes it sort of a user-friendly subset of dependent types, where the user doesn't have to do any sort of proof assistance. And Liquid Haskell can be used as a more powerful proof assistant, but I think in the common case, you can just let it do these deductions automatically for you. And that makes it very convenient to use, because all you have to do as a programmer is just specify preconditions, specify postconditions, then Liquid Haskell does the rest for you. But Liquid Haskell is not just there to help verify that your functions are correct. These refined types are also really effective tools for communicating information between programmers. So here I've given a mystery function with a refined type signature. And can anybody in the audience tell, just from the type signature, what this function is likely to be? Yes, that's correct. This is the split-at function from the base libraries. And you can't deduce what it is uniquely from the type, but the type gives a pretty strong hint. It tells you that it takes an integer named n, and then a list of a's named x's, and then it returns 2 lists. The first list, its length is n, so we know that in this case it's taking the first n elements of the list. The second list, r's, its length is the remainder of the list, so the length of the original list of x's minus n. And the refined type is adding preconditions to enforce that this n is in between 0 and the length of the x's, so we don't have an out-of-bounds error case that we have to handle in our function. So here's an example of how we would implement the split-at function and give it the refined type. So for the split-at function, we say, OK, if you split at index 0, well, then the first list you return is empty, and the second list you return is the remainder of the list. And so you can see that the split-at function, and then there's the inductive case, where if you split a non-empty list, well, then you just split the rest of the list at index n minus 1, and then attach the first element to the left result. Now, there's one case that in this pattern match that I have not handled when writing this function. Does anybody know what case that we're missing and not handling? Yes, well, close. So the list has to be empty, and n has to be non-zero. That's correct. So here's a question for the audience. Liquid Haskell is a totality checker, which does exhaustiveness checking for functions like these. Do you think Liquid Haskell will accept or reject this program? Who thinks it will accept? About half, a third to a half of the audience. Who think it will reject this program? About an eighth of the audience. OK, so people have a lot more confidence in Liquid Haskell, and the people who said accept are correct. Liquid Haskell's exhaustiveness checker will know from the precondition that we don't have to handle that last case, because it knows that if the list is empty, then n has to be in between 0 and 0. So n has to be 0, therefore it can't be non-zero. Therefore, this is an exhaustive pattern match. And we can just show Liquid Haskell. Sorry, let me close this. Checking that file. So liquid, turn on the totality checker, examples, split at, has to think a little bit, and then it says, OK, this is safe. Another cool feature about Liquid Haskell is that it supports type-level set and map operations. I'm only going to talk about set operations for this talk, but you can also do maps as well, which is very cool. So here's an example of the find function with a refined Liquid Haskell type. In this case, we actually already know from parametricity that the element that find returns has to have come from the list of values that you were searching. But in this, we're going to use this just to show an example of using type-level set membership in Liquid Haskell. So you can read this type as saying, find is a function that takes a predicate from A to bool, and then a list of x's to search, a list of a's to search named x's. And then it will return maybe a value of type A. If it does return a value named x, that x needs to be a member of the list of elements named x's. So this enforces that X came from the original list. And Liquid Haskell will verify that this type checks and satisfies that post condition. But here's an example where you wouldn't be able to deduce set membership from parametricity. So now I'm going to try to prove the opposite, that an element is not present in the final result using a delete function like the one from the standard libraries. So delete is a function that where you give it an element, and you give it a list, and it will delete all copies of that element from the list. And we can say that at the type level. So this takes an element X of type A and a list of A's, and then it returns a list of Z's such that X is not a member of the list of elements named Z's. And then the delete function, so actually, if I run this Liquid Haskell on this program, it's actually going to reject the program because there's a bug and the program doesn't match the specification. Can anybody spot what the bug is? Yes? That's correct. The last line has an X where there should be a Y. So we're actually inserting X into the list instead of deleting it. And the origin behind this example is that I've actually given this talk once before to a smaller group. And when I presented this example, I thought it was correct. And then they asked me to run the Liquid Haskell type checker on this example. The Liquid Haskell type checker rejects it. So we're all sitting there scratching our heads. What could be wrong here? Perhaps there's a bug in Liquid Haskell type checker. There are a lot of bugs in Liquid Haskell these days. And after a few minutes, we finally find the bug, and we realize the problem was between the keyboard and the chair. So Liquid Haskell does work, and it's very effective at what it does. And so you can see, let's just show you an example of that. So here we're going to do liquid on example/delete. It's going to reject it, and then, oops, apparently I have it open in another thing, whatever. You only live once. Oh, sorry, I'm opening the wrong file. Okay, so examples, delete. There we go. And then we run liquid. Now it accepts it. So it is actually checking that the element is in fact deleted from the list. So we know it's working. And what's really cool about Liquid Haskell is that you can teach it new tricks. You're not limited to built-in functionality, although it already supports a lot of built-in functionality, like type-level arithmetic, type-level sets, type-level maps. But let's say you want to add new functionality because there are some things that Liquid Haskell can't deduce from the code. This is very common when working with high-performance libraries like byte string or vectors, which may be using new GHC primitives or a code that has a foreign function interface to C code. So some things you just have to tell Liquid Haskell how it works. And you can basically add your new type-level symbols to Liquid Haskell's language using what are known as measures. So for example, I want to add a new type-level function called bslength, short for byte string length. And you just tell Liquid Haskell, the type of this type-level function is a function from byte strings to ints. This type-level function is not going to actually do anything. Liquid Haskell doesn't know anything about this function other than what you teach it via this assumption mechanism. So if I want to teach it something, I'll say, OK, I want to establish a connection between the term-level length function and this newly added type-level length function. So I'm going to assume that the length function on byte strings is the same as the type-level bslength function. And then once I've made that assumption, I can start using bslength as a refinement in type signatures. So if I can refine the type of the head function for byte strings to say that it now accepts non-empty byte strings, and Liquid Haskell will now check that at compile time for me. So one way you could use that check is as a runtime check. So I want to write a safe head function for byte strings, and I can just wrap that in if-then-else expression. So the condition of the if-then-else expression checks that the length of the byte string is greater than or equal to 1. Then that provides Liquid Haskell type-level information that the then branch of this expression is processing a byte string that has at least 1 byte in it. So then it knows the call to the head is safe, and then that will give us the safe result. And then for the other branch, we just return nothing, because we know statically that the byte string is going to be empty on that branch. But the whole purpose of using Liquid Haskell is that we want to get rid of runtime checks. We would rather transform them into static compile time checks whenever possible. And we can do so if we can teach it more things. For example, let's say I want to call head on a string literal hello world. And for people less familiar with Haskell, Haskell has support for promoting string literals to various types using the overloaded strings mechanism. So what's happening is that it's implicitly wrapping the string literal in a call to the bytestring.pack function. And so if we can teach Liquid Haskell how the pack function works, then Liquid Haskell can statically understand what's the length of this byte string. So here we say the pack function takes a list of characters named C's and returns a byte string named B's such that the length of the byte string has to equal the length of the characters. And then Liquid Haskell statically knows, okay, if this string literal is 13 characters long, and then we implicitly wrap it in a call to pack, then it must produce a byte string that's 13 characters long. Therefore, this is a safe call to head. So we have a static check that this is a safe call to head, and this returns a character instead of maybe a character. So at this point, you're probably wondering, okay, that's cute. Liquid Haskell can do lots of really nice things. What is it for, though? What am I most likely to use it in my day-to-day projects? And what I would like to propose is that the most killer use case for Liquid Haskell at the moment is statically catching out-of-bounds errors at compile time. And the main reasons why is that there's a lot of out-of-the-box support from this in Liquid Haskell's built-in refinements in the Liquid Haskell prelude. And this is a very well-trodden area of the compiler, so you're very likely to not run into bugs. Whereas if you try to use more advanced features of Liquid Haskell, you're much more likely to run into bugs. And it's very difficult to do using any other tool in the Haskell ecosystem. Because I find that most other approaches to compile time checks like this are either, well, first, either they're not compile time at all. In other words, they just give runtime exceptions. That's not what we want. Or they're inefficient, meaning that maybe they work on linked lists, but they don't work on vectors or byte strings or text or other high-performance data structures. Or they're brittle, meaning that they can prove very simple things, but the moment you try to do something really complex, then they can't deduce that the program is safe because they don't support type-level arithmetic. And then lastly, most other approaches require you to make some changes to your code to prove that your code is safe. Like I mentioned before, wrapping new types or changing your data structure. With Liquid Haskell, you just add preconditions, you add postconditions, your term-level code stays the same, and that's a very nice way to program. And as you learn Liquid Haskell, you're going to find that 20% of Liquid Haskell is learning how to prove things in it. It's pretty easy because in most cases, you just add preconditions, you add postconditions, and then the SMT solver does the rest of the work for you to prove your code is correct. The next 40% of learning Liquid Haskell is reporting bugs. I guarantee you're going to run into bugs. I know this because I think I have the record for the most number of bugs reported against Liquid Haskell, other than people who work for the research lab that maintains the project. And the last 40% is building a mental model of what Liquid Haskell can do and cannot do. And the truth is that Liquid Haskell is actually a very powerful tool. It can do much more than what I'm actually describing in this talk. And if you try to take advantage of those more advanced features, you're going to run into more bugs, have a worse user experience, but you can do a lot more. The lab that maintains this is always pushing the limits of what Liquid Haskell can do, so you should check out what they're working on because they're doing some very crazy stuff with Liquid Haskell to make it into a very expressive type system. But, and this also just makes it difficult in general to know like when you should apply Liquid Haskell to a problem and when you should not apply Liquid Haskell to a problem. Because there's always going to be the temptation when you learn something new to like, I want to apply this to everything in my code base and make it 100% safe. I advise just sticking to simple things like preventing out-of-bounds errors, and then that will give you a nice experience when using the tool. So I'm going to end the first section just by showing a simple example of turning runtime checks into compile time bounds checks. So here is a function that does a binary search on a sorted vector. So we're looking for the index of the last element less than or equal to a given element. So here's the element we're searching for in our sorted vector. Here's the actual vector right here. And then the way binary search typically works is every iteration of the search, you have a lower bound and an upper bound that you're searching. So I'm going to call these the min index and the max index of the vector, of the search function. And we can refine these indices. So for example, we know that the minimum index, it has to be less than 0. You don't want to go off the left end of the vector. And it has to be less than the length of the vector, so you don't want to go off the right end of the vector. And the upper bound, we know it has to be greater than the lower bound. Obviously, they should be, otherwise they're not upper and lower bounds. And it has to be less than or equal to the length of the vector. And then we can say that this will produce a result called index that has to be somewhere between the lower bounds. Otherwise, they're not bounds. And this last part right here is a little bit new. I haven't shown something like this before. So when I said that Liquid Haskell does all the work for you, there are some cases where it doesn't. So Liquid Haskell does have a totality checker. And the totality checker doesn't just check that you have non-exhaustive pattern matches. It also checks that recursive functions terminate. And the totality checker is pretty simple. In a lot of cases, it won't actually be able to prove that a function like search, which is recursive, will terminate. You have to give it a little bit of help. And the way you help it along is you just give it what's called a termination metric. It's some number that's guaranteed to decrease on every recursive call to your recursive function. So for our search function, we know that there's something that decreases every time it recursively calls itself, and that's the range that we're searching. Every time we're narrowing the range where our element might be. And we can teach Liquid Haskell that by just saying, okay, the maximum index minus the minimum index decreases on every recursive call. And then that's enough information for Liquid Haskell to do the rest. Then it says, oh yeah, now that you mentioned that, I can verify that your function is total and will eventually terminate. And then the actual implementation is pretty straightforward. So we first check, is the minimum index, so is the range between minimum index and the maximum index one element? If so, we're done. That's the result that we return. Otherwise, we divide the range into two, check the element in the middle of the range, and compare it to the element that we're searching for. If it's greater than the element that we're searching for, then search the lower half of the range. And then if it's less than the element we're searching for, recurse and search the top half of the range. And every time we test the element, we're going to use the unsafe index function from the vector library. So this function is unsafe for a reason, because it doesn't do a bounds check at all. And if you do have an out-of-bounds error, you're going to get a segmentation fault, which is very difficult to recover from. I don't think you can recover from a segmentation fault in a Haskell program. So, but in this case, the unsafe index function has a built-in refinement from the Liquid Haskell prelude that makes it safe. So we can't do an out-of-bounds call with it. So we can get high performance and safety at the same time. All right, so that concludes the Liquid Haskell basics part of the talk. Do people have any questions before I move on to the next part, showing examples from how we use it at work? Yes? Oh, sorry, I think they need to use the microphone first, sorry.
If I understand correctly what you told us, if I get data from an unsafe source, say I read it from a file or from a socket,
Yes.
I somehow have to establish some assumptions about this data. I mean, so I have to write a function which takes data, I know nothing about it, and results in data there I have some type level assumptions about it. And if this function can't assure those assumptions, what does it do?
So the question is, what if you can't prove at compile time that your data is safe, either because the data is from an untrusted source? Yeah, that's the main reason. So you do have to have at least one check, one runtime check in that case. But even then, and I'm going to show that in some of my later examples, you can still reduce the number of one-time checks so it's only one, as opposed to checking on in multiple places. So in some cases, you can't statically eliminate all checks, but you can get pretty close to just pushing all the checks to the very edge of your system. Any other questions before I continue? Yes. Oh, Oh, sorry. Yeah, go for it.
If we have several Haskell programmers and we let some of them use Liquid Haskell if they like, will these programs always compile and be as safe when we run them through the ordinary Haskell compiler without Liquid Haskell support?
So no, Liquid Haskell will not ensure that. The Liquid Haskell type refinements are only enforced by the Liquid Haskell type checker, not by the ordinary Haskell type checker. Liquid Haskell is not officially integrated into the Haskell compiler, which it should be, and I'm going to get to that's one way you can contribute to the ecosystem. But no, by default, if you're not running Liquid Haskell type checker on your code base, then you're not getting the benefits of these refined type signatures.
Thank you very much. Thank you very much. That was very exciting. It made me think of quick check. And one of the issues when you write quick check properties is you don't always get the properties right. Mm-hmm. I suspect about 50% of the time you're debugging the quick check property, and there you get a counterexample to help you do the debugging. And I was wondering how you debug Liquid Haskell properties.
So Liquid Haskell, so let's say that a property, well, there's two things there. One is, how do you verify that your assumptions, like the assumed type signatures, are correct? You can't. You just stare at them really hard. Or, so basically the point of that is you just localize the areas that you can introduce error. The second question is, let's say a property fails or the type checker gives you a bug. What next? Liquid Haskell technically does have support for counterexamples, but I tried using it a week ago when preparing for this talk, and it still didn't work. So this is an example of a bug that I ran into using Liquid Haskell. But in theory, it supports generating counterexamples from failed type errors. In practice, I find the way I debug these errors is just looking at the normal type error that Liquid Haskell emits, and then just trying to reason through what information Liquid Haskell was able to deduce, what precondition it was expecting, and then why it wasn't able to get from the deduced information to the expected information. Is that the last question? OK. So at Awake Security, we use Haskell for high-performance protocol parsing because we're a network security company. And for our purposes, libraries like binary and serial are not fast enough when trying to parse protocol-level data. So here's an example of how you might write a simple Haskell parser. So a parser of A's is, under the hood, usually equivalent to a function from a byte string where the input to the function is the byte string you're trying to parse. And the output of the function is the result, which is a maybe value. If the maybe is nothing, your parse failed. If it's a just, then it contains the result, which is a value of some type A, and then the remainder of the byte string that has not yet consumed as part of the parse. So an example of a parser we might write is one that just takes the first n elements of the byte string. We call this take. And so it takes an input byte string named B's. We're going to check the length of the byte string, see is it less than n. If it is, then we can't return n byte strings, so the parser fails and returns nothing. But if it is long enough, then we split the byte string using the split-out function. Then the first value returns is the n bytes that we wanted. The second value split-out returns is the remainder of the byte string we have not yet parsed. And so parsers can be functors and applicatives and monads. I'm not going to dig into those other than to point out that gives us do notation, which I'm going to use on the next slide. So let's say I'm trying to parse a UDP header. And if you're familiar with the UDP protocol, a UDP header has 4 2-byte fields. So the source port, the destination port, the length of the message, and a checksum. So we're going to define a UDP data type, and then we're going to add a comment to each of these fields saying this should be a byte string that's 2 bytes long. And the way we could parse a UDP header is we just call take2 4 times in a row. That gives us each field. And then we slurp them up into a record using Haskell's record wildcards extension. And this is a very inefficient way of doing things, because we're actually going to check the length of the byte string 8 times, twice for each take. And so here's an example of the core that this would generate if we just have GHC dump its core when it's compiling it. You can see there are a lot of takes inserted into this code, and this actually impacts performance significantly for our use case. If we benchmark this, it takes 38 nanoseconds to parse the UDP packet header. And we can actually do much better than that if we just make a few optimizations to our code. So for example, a UDP parser, so let's say I want to remove some of the length checks. So one place where we introduce length checks is in the take function. Every time we call take, we're checking the length of the input byte string before we hand it off to the next step. But we already know up front that our UDP header has to be at least 8 bytes. So why don't we just have one check at the very beginning that checks, are we 8 bytes long? And then after that check, we can just safely split it into 4 2-byte chunks and then slurp that up into our UDP record. So that gets rid of 4 of our length checks. But there are still 4 more that remain because this split-out function itself internally has a length check inside of it. So here's the core generated by that. It's a little bit different, but still not much more efficient. So here's how split-out is implemented internally for the byte string library. So just like our split-out function on lists, it has some preconditions on the input. But these are being enforced at runtime instead of at compile time. So here, it says that the length has to be, if it's less than 0, then it has a special case for how to handle that. And if it's greater than the length of the list, it has a special case for how to handle that. But the case we actually want is this last case where we're actually splitting the byte string. Because we know up front that our byte string is never going, our value n is never going to be out of the bounds of the list, because we already did the length check up front once, so we don't need to do it again. And we can eliminate these length checks in split-at if we use these unsafe functions called unsafe take and unsafe drop, which are like the analogous functions on lists, except very unsafe, because if you use them wrong, you're going to get a segmentation fault. So here's what the really efficient version of the code would look like, where we have only one length check, period. So we've replaced all our split-at functions with an unsafe split-at function, which under the hood uses unsafe take and unsafe drop to split the byte string into 2 halves. but this is very unsafe. So in this case, we didn't trust the compiler to optimize our code, which is why we're doing all these contortions to the code to make it fast. But I would like to at least be able to trust the compiler to check my work and verify that this is still safe, even if I'm not letting the compiler do the job of optimizing the code for me. And unsafe take do have preconditions. It's just that they exist as comments instead of as a type signature. So if you look, here's the comment for the unsafe function, which says it's a variety of take which omits the checks on n. So there's an obligation on the programmer to provide a proof that n is in between 0 and the length of the byte string. But I don't want there to be an obligation on the programmer because humans are error prone. I would like there to be an obligation on the compiler because the compiler is less error prone in the case of Liquid Haskell. And because documentation is not machine checked. So like before, we can teach Liquid Haskell to enforce these preconditions at compile time. So we introduce a measure for the byte string length, as in the previous slide. And then we have to assume things about the unsafe take function. This is the part where we can introduce human error. So we got to look at these very hard and make sure that they match the original comment. So it says unsafe take is a function that takes an integer named n, such that n is greater than 0. And then it takes an input byte string named I, such that n is less than or equal to the length of that byte string. And so that's the precondition that matches the original comment. But we can actually go a step further than the comment, and we can attach a postcondition, which says that we know the byte string we're going to get back is going to have exactly n characters, because n is exactly within bounds. So we statically know what the result is going to be. And we can do the exact same thing for unsafe drop. So we statically know what its output length is going to be. And then we can combine those both to generate a refined type for unsafe split at. That type, we don't need to assume anything, because we can derive the postcondition and preconditions from unsafe split at from the ones for unsafe take and unsafe drop. Just make sure how far I am. OK. We can also add refinements to the original UDP data type that we declared. So we can turn these comments into type level information as well, because Liquid Haskell lets you create refined data types. So I can now say each field is a byte string named bees, such that the length of bees is equal to 2. And so now Liquid Haskell will enforce at compile time that we have the right lengths of fields for this data type. And then we can verify that this code is safe. So let's do that. So liquid, totality, examples, parser. Okay, takes some time to think. Has to think about it, but it says, OK, this is definitely safe in this case. So what does safe mean in this context? So Liquid Haskell can only verify things that we teach it to verify. And the only things that we taught it to verify were that there were no out-of-bounds errors and that all the UDP fields are exactly 2 bytes long. But that's still pretty good. And if you want to add more information, you're free to do so. You can always extend these refined types to add new measures, add new preconditions, add new postconditions. Here's the original program. I'm going to tweet the link to these slides afterwards, and you can also find them on GitHub. I'll give a link at the end of this talk, so you can check this yourself if you're interested in doing so. And here's what the generated core looks like. So now it actually fits on one slide, which is great. And it looks like purely functional C code, really efficient, something that I would have probably written by hand if I knew how to program in core directly. I think the only thing I wouldn't have done by hand is subtract 2 4 times in a row here at the bottom, instead of subtracting 8. But other than that, this is pretty good tuned code for JC to generate for our example. Here you can see there's the one length check at the top. This is the only length check now. And now we can benchmark this to see how much performance improved. Now we can parse a UDP header in 6 nanoseconds instead of 38 nanoseconds. So that's a 6-fold improvement. And it's still totally safe. And we can also compare to how fast it would be if I used the serial library to parse the same thing. The serial library actually takes 120 nanoseconds. So we are 20 times faster than if we had just used a serial library. So this is an example of why we use Liquid Haskell and low-level byte string parsing primitives at Awake Security to get every last ounce of performance that we can get out of Haskell. So one thing we also believe strongly in Awake Security is that we should open source our work as much as possible. So we've actually taken a lot of our work on low-level byte string stuff and open sourced the refinements that we had and we upstreamed it into the Liquid Haskell prelude. So for example, we can see here are all the refinements. Oh, I need to have an internet connection. Oops. How difficult is it to get an internet connection on the spot? I would like to show a few things via the internet. Give it just a second. OK. Let's try again. Let me make that a little bit bigger. OK. Oops, too big. There. So here's an example of some refinements for the bystring library. So you can see like cons, you give it a word date and a bystring, and you know the result is going to be one more byte in the input. And we've done that for basically all the functions in every module in the bystring library. So if you use Liquid Haskell today, you benefit from these refinements out of the box, which is pretty cool. So that's the end of the practical example. That's as much as I can fit within the talk. Do you people have any more questions before we go on to the final section on ways to contribute? Yeah.
I was wondering whether Liquid Haskell can infer any preconditions or postconditions on itself without a programmer having to annotate anything.
Oh, can Liquid Haskell, can it do some things without annotation from the programmer? The answer is yes. So for programs defined using basic Haskell features like data types, pattern matching, and so forth, Liquid Haskell will actually generate some automatic refinements under the hood. And you can even promote such functions automatically to the type level. And Liquid Haskell supports that. So yes, Liquid Haskell does do some things automatically out of the box for you. Yes?
What's the recommended way of distributing these refinements, like the ones that you just made? I mean, should they just be integrated into the main libraries and be part of the main libraries on HaskellX, or is there a separate repository, or is there anything that Liquid Haskell developers themselves are proposing for this?
So currently, the only way that I know of is you have to add it to the Liquid Haskell prelude. Nikki, one of the people who works on Liquid Haskell, told me that they would like a way to integrate this into GHC such that your programs would automatically pick up refinements from modules that you depend on, but it currently does not support this as far as I know.
What kind of overhead does this add to compilation times?
Quite a bit, actually. So Liquid Haskell type checker, it takes quite a long time on large modules. So one ways that you contribute is to help improve the performance of the type checker, but it does take a substantial amount of time to type check some modules.
In your recursive example, you gave a termination measure, right? Something that was strictly decreasing, but also type int, right? So it's not an actual number, so it's not something that is guaranteed to reach 0. So does it combine it with the pre and post conditions to say, well, this is actually terminating, or does it assume it's an actual number?
I actually don't know the answer to that question. In this case, it does know that the upper bound minus lower bound is a natural number, because we had something in the type that enforced that the upper bound was greater than the lower bound. I don't know if Liquid Haskell was using that information specifically. I don't actually know for sure if Liquid Haskell requires the termination condition to be a natural number, although I think it probably does. So I'm going to guess the answer is probably yes, meaning that it probably does require it to be a natural number. And in this case, it was able to infer that the termination condition was a natural number.
So I'm wondering, there are certain instances that lists have, but non-empty lists have more instances. For example, they're comonads. Mm-hmm. Do you know how that might interact with the Liquid Haskell preprocessor?
Wait, I didn't understand the question.
So the refined type, strictly speaking, has more instances, or has certain instances that the non-refined type does not have. Mm-hmm. Would you imagine that you would create a new type to give it those instances, or could you imagine a way of being able to get the comonad instance without having to add new data types? Or
so the Liquid Haskell. So first off, Liquid Haskell information is not available to the ordinary GHC type checker. So if something was something was only a monad, if it were refined, there's no way you could get GHC to understand that. As far as to what data types you can hang Liquid Haskell refinements, off of. If you want to hang a refinement off a data type, you got to define one. But I'm not aware of any other restrictions around that.
After the first length check, here, Gabriel.
Oh, yeah.
After the first length check, Liquid Haskell knows statically that the length of the list is less than 8. why then does it not eliminate all the other length checks automatically in the core program? Why do you have to do it yourself and then verify you've done the correct thing rather than use this information you already have?
The reason why is because Liquid Haskell is purely a type checker. Liquid Haskell is not a replacement for GHC's code core generation or code generation step. So the information that Liquid Haskell is able to deduce is not available to the GHC optimizer, which is one reason why it would be better if we could integrate Liquid Haskell with the GHC optimizer. But yeah, that information is not available to it, so it can't know that it can eliminate these length checks when it's optimizing.
Thank you. Nice talk. I sort of like the, let's say, non-intrusiveness of your approach with the comments. Is that something that you decided for from the get-go? And to what extent do you want to stick to that, or to what extent is your plan to actually get more of the stuff that you can get with Liquid Haskell with GHG itself?
So the question, I still didn't quite understand the question.
Okay, I suppose my question was, I like the fact that that it's like just comments, which I think helps with the adaptation. But is that something that you wanna stick for, or is your plan or your wish that you want to get more of the features and the things that you get with Liquid Haskell like leak into GHC, so to say?
So I'm not a core maintainer of Liquid Haskell, I'm just an evangelist. But my understanding is they would like to integrate this more with GHC so that the Liquid Haskell type signature wouldn't have to exist as a comment. The best case scenario would be that the ordinary GHC type signature could have these refinements. But that would require a significant amount of work to upstream this into GHC. I think, yeah.
So most of the added information is in terms of integers.
Mm-hmm.
Do you have any examples where you use non-integer type of extra data that you carry around in the program?
You mean other numeric types or just other types?
Just other types.
So the only things that Liquid Haskell has built-in support for is numbers, sets, which can be derived from lists, and maps. Anything else, you have to create it yourself using either the measure system or Liquid Haskell support for automatically promoting some types of code defined using pattern matching and so forth. So yes, you can promote code that just uses ordinary data types and pattern matching features. I haven't shown that in this talk, but it's something you can do. Yeah, so you can do it, I just haven't shown how to do it.
In your examples, you had the runtime check function, which I suppose is run at runtime, but you just said that the code generated by Liquid Haskell is not accessible in GHC. So I just don't understand, the final program is compiled by Liquid Haskell or GHC?
The program is compiled by GHC, not by Liquid Haskell. So I, the programmer, eliminated all the length checks in the code. So I did basically the work of optimization for GHC. So Liquid Haskell didn't transform my code in any way. It just made sure that the hand-rolled optimizations I was doing were safe because they rely on removing bounds checks and doing other unsafe things.
Is there a way of demoting quick check expressions to Liquid Haskell or promoting the other way around, so we can make use of existing quick checks to put them into Liquid Haskell, or to make Liquid Haskell expressions into quick check expressions that we can use quick check to find those corner cases?
As far as I know, there is no integration or tooling to automatically convert between quick check property checks and Liquid Haskell refined types. Maybe there is, but I'm not aware of it.
In the early part of the talk, you said Liquid Haskell can be used for avoiding new types. But is it just new types where you annotate like, this is a non-empty thing, or let's say we have currencies or something like this. Could you use Liquid Haskell for annotating values for what they are?
Yes. So like, let's say you, a really common example of this would be like, let's say you have a, I don't know if people are familiar with the paper trees that grow, for like how you basically take a tree and you can like turn on certain constructors in a type. That's a very common use case of where you want to like, you know, slightly refine a type. So let's say you have some sum type with 10 cases, and in some parts of the code, you want to make only certain cases possible. So like at least you want to turn off, you know, the first 2 cases or, you know, the third case. You can do that with Liquid Haskell. You just take a type and you can say like, it cannot be, for this particular input, it cannot be this case, or it cannot be this case, or it cannot be that case. So that's an example of how you can just like take a value and you can just start subtracting cases from it. Or you can also tag a value. Like you can just say like this value, like you mentioned currency, right? You can just say, treat this integer as a, actually let me think about that. So the way you would do currency, I'm not sure if this is better than the new type approach, is you create a measure of the currency. So the measure of is currency. It's a function from integer to bool. And basically you would refine an integer with that measure, saying you have an input n of type integer such that is currency n. And then that would be a way that you could get equivalent behavior to what you would get with a new type. I'm not sure that's an improvement though. Okay, I'll continue. So Liquid Haskell has a prelude of refined types for common libraries. So I showed an example of that before for the by-string case. One way you can very easily contribute to Liquid Haskell is just adding more refinements to this prelude. So one place that has a lot of low-hanging fruit is the refinements for the vector library. So here I can open up the data.vector module, and you can see actually that's it. So at one point, I actually added a refinement for the indexed map function for vectors, but I never actually added a refinement for just the ordinary map function for vectors. So if I wanted to like add such a refinement, I could just go to open it up on GitHub, edit it, copy, paste. You know, map is now ordinary map. And now I can create a PR refining map to say that it's length preserving. So the output of the map function is the same as the input vector that you feed to it. And then that is how easy it is to, you know, add map refinement for vector. And then I can create a PR for that. And then hopefully Liquid Haskell CI doesn't reject it. And then so this is my very crude IDE is my browser. And then that's how easy it is to make a contribution. So you could literally do it as you're watching my talk if you're interested in doing so. Another way you can contribute is just report bugs. So Liquid Haskell does have a very large test suite, but what they're trying to do is very ambitious, and they have to support a lot of GHC extensions when they're type checking code. So if you can report bugs, then that's very valuable, and they are very appreciative of these reports, and they're very active at responding to them too. If you are somebody who's familiar with Stackage or a package author or a maintainer, one way you can contribute is to help get Liquid Haskell on Stackage. For example, some of its dependencies are old, like ESON, and they need to be upgraded to newer versions. Or some of its dependencies are not on Stackage yet, like the Liquid Fixed Point library. So just helping contribute getting those dependencies up to date on Stackage would make it easier for other people to use it, because then they could just say stack install Liquid Haskell, and they wouldn't have to worry about like getting the right versions of certain dependencies correct. If you are familiar with other package managers like Brew or Debian or Arch, I actually don't know what the package manager for Arch is. You can actually just create packages for installing Liquid Haskell using your favorite package manager. And if you can, it would be nice if you could also install an SMT solver along with it, so the user doesn't have to figure out how to install something like Z3 if they want to use Liquid Haskell. If you're willing to, you can try to help triage or fix issues. I think there were 238 issues last time I checked. You can do things like, well, obviously you can fix the issue if you can. They would definitely welcome that. Or even just turning bug reports into failing tests is a very valuable contribution. Finding stale issues that have already been fixed is another way that helps reduce their maintenance load. if you are, as one person asked, performance is an issue. So if you start using Liquid Haskell on larger programs, it takes much longer to type check them. So if you can, one way you can contribute is figuring out ways to speed up the type checker, or generates constraints that are easier for the SMT solver to solve quickly, for example. And then one long-term goal of Liquid Haskell is to integrate directly with GHC. It's a very challenging but worthwhile project, but it involves a lot of work. You have to draft a formal proposal for what that integration would look like, figure out a way to reconcile Liquid Haskell with GHC's upcoming support for dependent types. And if you want to distribute it with GHC, then you need to figure out a way to package an SMT solver with GHC as well. But this would be a very worthwhile thing to do. Going back to the original goal of the talk, we want to push as much things upstream as possible. Why not push Liquid Haskell upstream directly into the GHC compiler? Any questions before I go on to, with some concluding remarks? Okay. So the things I want you to walk away from this talk is that Liquid Haskell works very well for ensuring the safety of high-performance code like vector or bystring or text. They could benefit from your help. So if you would like to volunteer, you think this is a high-impact project for the Haskell ecosystem, this is a great way that you can contribute. And I have some slides at the end. I don't know how much time we have left, but I can also show how you can integrate this with Cabal or Stack projects if people are interested. These slides are available online. I have a slides repository, which includes these slides in Markdown form, so you can easily go back to this after the talk. I'll also tweet this from my account if you want to find the link to the slides as well. And I think that concludes the talk. And these slides also contain instructions on how you can install Liquid Haskell using Stack, how you can get it into in a Nix shell if you just want to try it out really quickly, and how you can integrate it into Cabal or Stack projects just by modifying your setup.hs file. And I think that's it.